Sketch the graph of the function f of x equals x times the square root of 32 minus x squared by determining the parts a through I. F of x equals x, a polynomial term, the domain will be all real numbers, times the square root, an even root, of 32 minus x squared. We can rewrite the square root as a fractional exponent. It will be 32 minus x squared to the first power second root 1/2 power. The denominator of a fractional exponent is the root. It's an even number here, and the domain of an even root is not necessarily all real numbers. The domain requires that what is inside of an even root has to stay greater than or equal to 0. So 32 minus x squared has to stay greater than or equal to 0. We can solve for x by subtracting 32 from both sides, so negative x squared is greater than or equal to negative 32. Divide both sides by a negative 1. This will flip the inequality. We can then take the square root of both sides. The square root of x squared is the absolute value of x. The square root of 32 can be reduced because 32 is a perfect square 16 times 2, and the 16 can come out of the square root as a 4. Since the absolute value of x is less than or equal to 4 square root of 2, we can remove the absolute value symbols by putting it between a negative 4 square root of 2 and a positive 4 square root of 2. So for part A, the domain begins at and includes square bracket negative 4 square root of 2 up to positive 4 square root of 2 also includes its square bracket. For part B, we want to determine if there is any symmetry. This is done by evaluating f of negative x and comparing it to the original function f of x. F of x inside the square root is made up of a constant which always has y-axis or even symmetry, subtracting an even power which also has y-axis or even symmetry. Since the two match, this entire portion will have y-axis or even symmetry, times the x, which is an implied first power, odd power, it will have origin or odd symmetry. Odd times even is odd. So f of x will have origin or odd symmetry. F of negative x is negative x times the square root of 32 minus a negative x squared, which is negative x times the square root of 32 minus a negative squared is positive, and then x squared. Comparing this to the original, it is exactly the same as the original, except with a negative in front of it. So f of negative x equals negative f of x, which is the condition needed to have origin, also known as odd symmetry. This means that the graph will be its own mirror image over the y-axis followed by the x-axis. We will be sure that that is the case. For part C, we want to determine the y-intercept. This is the point where the graph crosses the y-axis, defined by x equals 0. We can find the corresponding y-coordinate by plugging the x-coordinate back into the original function, y equals f of 0, which is 0 times the square root of 32 minus 0 squared, which is 0 times the square root of 0 squared is 0, 32 minus 0 is 32. 0 times anything is 0. We had an x-coordinate of 0, we found a corresponding y-coordinate of 0, so 0, 0, the origin will be the y-intercept. For part D, we want to determine the x-intercepts. These are the points where the graph crosses the x-axis, defined by y equals 0. Y, which is f of x, can be set to be 0. And we can solve for all x's. Because of the x in front of the root, that tells us that x equals 0. Because of the root, what's inside the root has to equal 0, so 32 minus x squared equals 0. We can solve for x by subtracting 32 from both sides. Dividing both sides by a negative, these will both become positive. Taking the square root of both sides, x equals plus or minus square root of 32. 32 is a perfect square, 16 times 2. The 16 can come out as a 4, so plus or minus 4 square roots of 2. We had a y-coordinate of 0. We found 3 corresponding x-coordinates. We compare them off with the y-coordinate of 0. So we have 0, 0, positive 4 square root of 2, 0, and negative 4 square root of 2, 0. For part E, we want to determine any vertical asymptotes. F of x is a polynomial term times an even root. There is no denominator, so there will be none. For part F, we want to determine any holes in the graph. F of x has no denominator, so there will be none. For part G, we want to determine the end behavior, horizontal asymptotes or slant asymptotes. F of x is a polynomial term times an even root, so it has no denominator, it will have no horizontal asymptotes or slant asymptotes. But because of the even root, it has left end and right end behaviors according to the domain. Up here, the domain includes a left end and right end. They will both be an endpoint. The left end behavior will be an endpoint from the domain. It includes, and it will have an x value of negative 4 square root of 2. That's its x-coordinate. And it has a corresponding y-coordinate, which can be found by plugging the x-coordinate back into the original function. So the corresponding y-coordinate will be f of negative 4 square root of 2, which will be negative 4 square root of 2 times the square root of 32 minus negative 4 square roots of 2 squared, which is negative 4 square roots of 2 times the square root of 32 minus, a negative squared is a positive, 4 squared is 16, root 2 squared is 2, 16 times 2 is 32. So it's a positive 32 with a negative in front of it. 32 minus 32 is 0, square root of 0 is 0, 0 times anything is 0, all this will equal 0, so it has a corresponding y-coordinate of 0. For the right end, from the domain, it's also included, it will be an endpoint. It has an x value of positive 4 square roots of 2. That'll be the x-coordinate. We can find the corresponding y-coordinate by plugging the x-coordinate back into the original function. So y will be f of positive 4 square roots of 2, which will be positive 4 square roots of 2 times the square root of 32 minus positive 4 square roots of 2 squared, which is 4 square root of 2 times square root of 32 minus 4 squared is 16, square root of 2 squared is 2, 16 times 2 is 32. 32 minus 32 is 0, square root of 0 is 0, 0 times anything is 0. So we also have a corresponding y-coordinate of 0. The left end and right end endpoints are 2 of the x-intercepts. So not a surprise, we found the corresponding y-coordinate to be 0 for each of those. For part H, we want to determine the intervals of trend, relative maxima, relative minima, plateaus, and cliffs. All of this involves the first derivative, f prime of x. We'll take the first derivative from the original function version where it's written as a fractional exponent, this one here. Notice that f of x is the product of 2 expressions, so it will require a product rule. We'll need a little bit of room to work out the derivative here. We can use another page. So f of x is x times 32 minus x squared to the 1/2 power. The first derivative will make use of the product rule. Derivative of the first, which will be a 1, times the second left alone, plus the first left alone, x, times the derivative of the second, which will be a power rule. Bring the power down, leave the inside alone. subtract 1 from the power, I will call that 2 halves, and then multiply by the derivative of the inside to complete the chain rule. For the first term, we have 1 times an expression. 1 times anything is that same thing. For the second term, we can bring the constants together. We have a 1/2 and a -2. We can multiply the numerators. 1 times -2 is -2 over the denominator 2. -2 over 2 can reduce to a -1. So it'll be a -1, the 1's implied. We have an x and another x. X times x is x squared. And we have a 32 minus x squared to the 1 minus 2 -1/2 power. We want to fully factor the first derivative. There is a common factor of a power of 32 minus x squared. We have it to the 1/2 power and the -1/2 power. We can factor out the lower of the two powers. That will be the -1/2. It's lower by being negative. So 32 minus x squared to the -1/2 power factored out. Factoring is division. Division is subtraction of exponents. So by factoring out a -1/2 power, we will be subtracting a -1/2, which is equivalent to adding a 1/2 to each of the powers. Adding 1/2 to this first power, 1/2 plus 1/2 is 2 halves or 1, will become a power of 1, and we will have 32 minus x squared left over. Adding 1/2 to this power, -1/2 plus 1/2 is 0. We have a power of 0. Anything raised to 0 is a 1, and we will have a minus x squared left over. So after factoring, we will have a 32 minus x squared minus another x squared. (32 minus x squared minus another x squared). We can combine like terms together inside the square brackets and turn them into parentheses. We have a 32 minus x squared minus another x squared will be a minus 2x squared. We want all powers to be positive, so the -1/2 power can move to the denominator to become a positive 1/2 power. The 32 minus 2x squared will stay in the numerator. The 32 minus x squared will move to the denominator to become a positive 1/2 power. We can rewrite the positive 1/2 power as the square root. We do want to fully factor the first derivative. In the numerator, there's a common factor of 2. Factoring that out will leave behind a 16 and a minus x squared. And the 16 minus x squared is a difference of squares and can factor further. 4 plus x and 4 minus x. In the denominator, the 32 minus x squared is inside of an even root, a square root, and it doesn't need to be factored. So we have the first derivative written as a single fraction. All powers are positive, and it is fully factored, at least the portion that is not inside of an even root. So this is the version of the first derivative we will want. So it was found to be 2 times 4 plus x times 4 minus x divided by the square root of 32 minus x squared. Since we have it written as a single fraction, all powers are positive and it's fully factored, we can now set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. From the numerator, it's already factored, so we can see from the 4 plus x factor, we get x equals -4. And from the 4 minus x factor, we get x equals +4. From the denominator, we have 32 minus x squared equals 0. We can subtract 32 from both sides. Divide both sides by a negative. These will both become positive. Take the square root of both sides, which will give plus or minus the square root of 32. 32 is a perfect square. 16 times 2. The 16 can come out as a 4, so this will be plus or minus 4 square root of 2. So we have an x equals positive 4 square root of 2, and we have an x equals negative 4 square root of 2. We will now check to see which of these x values are in the domain. The domain is all real numbers between and including negative 4 square root of 2 and positive 4 square root of 2. 4 times the square root of 2. Square root of 2 is 1.4 approximately, times the 4 will be about 5.6. So the domain is about negative 5.6 up to positive 5.6, and therefore it will contain the negative 4 and positive 4. And it will certainly contain the positive 4 square root of 2 and the negative 4 square root of 2 because they are the endpoints, and it does include the endpoints. So all 4 of these are included. All 4 of these are critical numbers. We can now draw a domain line, a line representing the domain. It has a left endpoint and a right endpoint that are included. However, we found each of them to be a critical number, and they will be removed. So it will be round brackets on each end. And it's negative 4 square roots of 2 up to positive 4 square roots of 2. We can put all of their critical numbers on here in order. We have a negative 4. We have a positive 4, which splits the domain interval into 3 separate intervals. We can pick a test value in each of the intervals. 4 times the square root of 2 is about 5.6. So the first interval, negative 4 square root of 2 to negative 4, negative 5.6 to negative 4, negative 5 is in there. The next interval, negative 4 to positive 4, 0 is in there. Next interval, 4 to positive 4 square root of 2, or positive 5.6. 4 to 5.65 will be in there. We can now test the trend by plugging the test values into the first derivative. We only care whether it is positive or negative, so the best place to plug in will be the fully factored version. This version here. A couple of things about this. In the denominator, the 32 minus x squared that's inside of the square root, from the domain back up top, is required to stay greater than or equal to 0, and it only equals 0 at the left and right endpoints. So it will be greater than 0. It's a positive number, and the square root of a positive number is a positive number, so that entire denominator is a positive and will not affect the positive or negative of the overall first derivative. And the 2 in the numerator is also a positive. So the only portion that matters for the positive or negative of the first derivative is the 4 plus x and the 4 minus x. That's what we need to plug into. Starting with the test value of negative 5, 4 plus a negative 5 is a negative. 4 minus a negative 5 is 4 plus 5, which is a positive. Negative times positive is negative. We have a negative first derivative. This corresponds to a decreasing trend. Plugging the test value of 0 into the portion of the first derivative that matters. 4 plus 0 is positive. 4 minus 0 is also positive. Positive times positive is positive. We have a positive first derivative, and this corresponds to an increasing trend. Plug in a positive 5 into the portion of the first derivative that matters. 4 plus 5 is positive. 4 minus 5 is negative. Positive times negative is negative. We have a negative first derivative. This corresponds to a decreasing trend. Right at the critical number of the left endpoint, negative 4 square root of 2, we did have that as a critical number. It is a left endpoint, so there is no graph to the left of it, but to the right of it, it is decreasing, and that makes x equals negative 4 square root of 2 be a relative maximum. That critical number did come from the denominator being set equal to 0. And therefore, it's not a normal relative maximum. It will be a cusp maximum. So we have a cusp maximum occurring at an x-coordinate of negative 4 square roots of 2. We can find the corresponding y-coordinate by plugging the x-coordinate back into the original function. That's been done already up here because it is the left endpoint. and we found a corresponding y-coordinate of 0. Right at the critical number of x equals -4, we have the trend change from decreasing to increasing, so x equals -4 will be a relative minimum. It came from the numerator for the critical number, so it'll be a normal relative minimum. It has an x-coordinate of -4 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of -4, which is -4 times the square root of 32 minus -4 squared, which is -4 times the square root of 32 minus, a negative squared is positive, 4 squared is 16. 32 minus 16 is 16. The square root of 16 is a 4, and -4 times 4 is a -16. So we have a corresponding y-coordinate of -16. Right at the critical number of x equals +4, we have the trend change from increasing to decreasing, so x equals +4 will be a relative maximum. X equals +4 also came from the numerator, so it'll be a normal relative maximum. It has an x-coordinate of +4 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function, so y equals f of 4, which is 4 times the square root of 32 minus 4 squared, which is 4 times the square root of 32 minus 4 squared is a 16, which is 4 times the square root of 16. Square root of 16 is a 4. 4 times 4 is 16. So I have a corresponding y-coordinate of +16. Right at the critical number of x equals +4 square roots of 2, that was also a critical number, and it's the right endpoint. We have no graph to the right of it, but to the left of it, it is decreasing. So x equals +4 square roots of 2 will be a relative minimum. But because it came from the denominator, it will not be a normal relative minimum. It will be a relative cusp minimum. So we have a cusp minimum occurring at an x-coordinate of +4 square roots of 2 and a corresponding y-coordinate to be found by plugging the x-coordinate back into the original function. We've done that already up here because it was the right endpoint, and we found the y-coordinate to be a 0. For part I, we want to determine the intervals of concavity and any inflection points. All of this will involve the second derivative, f double prime of x. We will take this from the first derivative, but we do not want to use the fully factored version. We will need a little more room for working out the second derivative as well, so we can go to the other page again for this. F double prime of x equals. It's best not to use the fully factored version because it's a product on the numerator, and because it has a denominator, it's a quotient, and we would have a combined product rule and quotient rule, which would be extremely messy. The best place to work it out is this one here, because this is just a single product rule. Derivative of the first is a power rule. Bring the power down. Leave the inside alone. Subtract 1 from the power. I will call that 2/2. And then multiply by the derivative of the inside to complete the chain rule, times the second left alone, plus the first left alone, times the derivative of the second, which will be a -4x. For the first term, we can put all the constants together. everything's multiplied here. We have a negative 1/2 and a negative 2. We can multiply the numerators. Negative 1 times negative 2 is positive 2 over the denominator 2. 2 over 2 is a 1. There will be an implied positive 1. We also have an x. There is a 32 minus x squared to the minus 1 minus 2 minus 3/2 power. And there's a 32 minus 2x squared. For the second term, we can move the constant out front, negative 4, and there's also an x, so negative 4x. And there is a 32 minus x squared to the negative 1/2 power. We want to fully factor the second derivative. There's a common factor of x in each term, as well as a power of 32 minus x squared. And we can factor out the lower of the two powers, and that will be the negative 3/2. It's lower by being more negative. So we can factor out an x and a 32 minus x squared to the negative 3/2 power. Factoring the x out, we'll take both of the x's out. Factoring out a negative 3/2 power, factoring is division. Division is subtraction of exponents, so we will be subtracting a negative 3/2, which is equivalent to adding a 3/2 to each of the powers. For the first power, negative 3/2 plus 3/2 will become a 0. Anything raised to 0 is equal to 1. All of that will become a 1, and there's what we have left, just a 32 minus 2x squared. For the second term, adding a 3/2 to the power, negative 1/2 plus 3/2 is 2/2 or 1. All of this will become a power of 1. And so we have a negative 4 times 32 minus x squared. There's what will be left after factoring. So we have a 32 minus 2x squared. And we have a negative 4 and a 32 minus x squared to the first power. So we have an x, we have a 32 minus x squared to the negative 3/2 power. Inside the square brackets for the first parenthesis, we can remove the parentheses by distributing an implied positive 1 in, which does not change the terms at all, 32 minus 2x squared. And for the second parentheses set, we can distribute a negative 4 in. Negative 4 times 32 is negative 128, and then plus 4x squared. So we have an x, we have a 32 minus x squared to the negative 3/2. We can combine like terms together inside of the square brackets and then write them as parentheses. We have a negative 2x squared and a positive 4x squared. Negative 2 plus 4 is 2, so we have a 2x squared. And we have a 32 minus 128, which is a negative 96. We want all powers to be positive, so we're going to move the negative 3/2 power to the denominator to become a positive 3/2 power. The x will stay in the numerator. The 2x squared minus 96 will stay in the numerator. And the 32 minus x squared will move to the denominator to become a positive 3/2 power. We want to fully factor the second derivative. There's a common factor of 2 in the numerator. We can factor it out with the x, and that will leave behind x squared minus 48. We'll leave the denominator alone. X squared minus 48 is a difference of squares if we think of 48 as the square root of 48 squared, because 48 is not a perfect square. But it still can factor using roots into x plus square root of 48 and x minus square root of 48. The denominator we will not need to factor because it's inside of an even root. The denominator of the fractional exponent is the root, and it's an even number here. The square root of 48 is the square root of a perfect square 16 times 3, and 16 can come out of the square root of a 4. So this also can be written as 2x times x plus 4 square root of 3 times x minus 4 square root of 3, and then the entire thing divided by 32 minus x squared to the 3/2 power. There's the version of the second derivative we're going to want. So it was 2x times x plus 4 square root of 3 times x minus 4 square root of 3, and then the entire thing was divided by 32 minus x squared to the 3/2 power. And now we can have our second derivative as a single fraction. All powers are positive. It's fully factored, so that we can set the numerator equal to 0 and we can set the denominator equal to 0 separately and solve for all x's. In the numerator, because it's factored, we can see from the factor x equals 0. From the factor x plus 4 square root of 3, we have x equals the negative 4 square root of 3. From the factor x minus 4 square root of 3, we have x equals positive 4 square root of 3. In the denominator, we have a 32 minus x squared inside of a power has to equal 0, so what's inside the power? 32 minus x squared has to equal 0. We can solve for x by subtracting 32 from both sides, dividing both sides by a negative, so x squared equals positive 32, and then take the square root of both sides, and x will equal plus or minus the square root of 32. 32 is a perfect square 16 times 2. The 16 come out as a 4. So x equals positive 4 square root of 2, and x equals negative 4 square root of 2. We'll now check to see which of these are in the domain. The domain is all real numbers from negative 4 square root of 2 to positive 4 square root of 2, including the ends. 0 is in there, so we keep that. It will be a candidate number. 4 times the square root of 3 is bigger than 4 times the square root of 2, because the square root of 3 is bigger than the square root of 2. So this is 2 negative, and this is 2 positive, and neither of those will be in the domain and are not candidate numbers. So we will cross each of those out. And then 4 square root of 2 and negative 4 square root of 2 are the left and right endpoints. They are in the domain because it includes them square brackets, so they are candidate numbers. We can now draw a domain line. It has a left end that's included, and it's negative 4 square root of 2, but we did find that to be a candidate number, so it will not be included, and it will be round bracket. Same thing with the right endpoint. It's included, but we found it to be a candidate number, so it's removed and not included round bracket on that end. We can put all other candidate numbers on here in order. The only other one that we have is x equals 0. This splits the domain interval into two separate intervals. We can test the concavity in each of these intervals. We need a test value in each. The first interval, negative 4 square root of 2, which is about negative 5.6 to 0, we can pick negative 1 in there. And then 0 to 4 square root of 2, or positive 5.6, we can pick positive 1 in there. And we can test the concavity by plugging the test values into the second derivative. We only care whether it is positive or negative, so we'll plug into the fully factored version. That's this version here. A couple things about this. The denominator, once again, we have a 32 minus x squared, which from the domain up top is required to stay greater than or equal to 0. And it's only equal to 0. At the endpoints, it's going to be greater than 0. It's a positive number. The entire denominator is positive. And it will not affect whether the second derivative is positive or negative. Also, the 2 in the numerator is positive. So the portion of the second derivative that will determine if it is positive or negative is the set of three things. Plugging in a negative 1, we'll have a negative 1 times a negative 1 plus 4 square root of 3, which will be a positive, times a negative 1 minus 4 square root of 3, which will be a negative. We have a negative times a positive times a negative. That's a double negative. It's a positive. We have a positive second derivative, which corresponds to concave up. Plugging in a test value of positive 1 to the portion of the second derivative that matters, positive 1 times positive 1 plus 4 square root of 3, which will be a positive, times positive 1 minus 4 square root of 3, which will be a negative. Positive times negative. It has only one negative. It will be negative. We have a negative second derivative. This corresponds to concave down. Right at the candidate number of x equals 0, we have the concavity changing from concave up to concave down. So x equals 0 will be an inflection point. It has an x-coordinate of 0, and it has a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of 0. Plugging into the original function will give 0 times the square root of 32 minus 0 squared, which is 0 times the square root of 0 squared is 0, 32 minus 0 is 32, 0 times the square root of 32 is 0. We have a corresponding y-coordinate of 0. Not a surprise because we found that to be the y-intercept as well as one of the x-intercepts. We can now draw the graph. We have a vertical axis and a horizontal axis. We have the domain just between negative 4 square root of 2 and positive 4 square root of 2. It includes the left and right. And we found the left and right to be endpoints. We can graph those. So the left endpoint, we will label it. We found to be negative 4 square root of 2, comma 0. The right endpoint, it'll be the same distance away from the origin, but on the right side, so somewhere about right here. We can label that one as well. So that'll be 4 square root of 2, comma 0. We have origin or odd symmetry, and that means that the graph will be a mirror image of itself over the y-axis followed by the x-axis. We'll make sure that that is the case. We have a y-intercept of the origin. That's here. We can label it And we had three x-intercepts. The origin, when it passes through the origin, it passes through both the x and the y, so not a surprise that's also an x-intercept. And we also have the left and right endpoints. We've already graphed and labeled those. So all the intercepts are accounted for. We have no vertical asymptotes, no holes. We've accounted for the endpoints already. Right at the point that's the left endpoint of -4 squared of 2, 0, we have a cusp maximum. But because it's a left endpoint, it's not going to be a full cusp maximum because no graph will exist to the left of it. So it'll just be the right side of a cusp maximum. A full cusp maximum at that endpoint would look like this, but we're going to only have the right portion of it. Cusp means that it has a vertical tangent. It's vertical right at the left endpoint, and then it will start to turn from there. So it'll look something like that. Right at the point of -4, -16, we have a relative minimum. So that will be down here somewhere, maybe approximately right here. We'll label it as -4, -16. And this will have the shape of a relative minimum. So it looks something like that. Right at the point of 4, 16, we have a relative maximum, so that will be up here. Approximately right here. And we can give it a shape of a relative maximum like so, and label that. That's at 4, +16. And then right at the point 4 squared of 2, 0, which is the right endpoint, we have it as a cusp minimum. It will be only the left portion of a cusp minimum because no graph will exist to the right of the right endpoint. So it'll be the left half of a cusp minimum. Cusp means that it will be vertical tangent. It'll be vertical at first, then it'll curve from there, like so. And then right at the point 0, 0, the origin, we have an inflection point. To the left of it, it is concave up, and to the right of it, it is concave down. So we can indicate that changeover from being concave up to being concave down, like so. And now we can connect these pieces together. So here we're decreasing and concave up, so it's curving upward while heading downward. Here it's increasing while still being concave up, so it's headed up and curving up. Here it's increasing and concave down, so it's headed up, but it's curving downward. And here it's decreasing and concave down, so it's headed down and curving down. So it's following the domain. It only exists between -4 squared of 2 and +4 squared of 2, including the endpoints. And it is following the origin odd symmetry like it should. If we reflect this over the y-axis, which will make it look something like so, and then reflect it followed by over the x-axis, it will reflect and end up upside down and completely line up with itself. So it is its own mirror image over the y-axis followed by the x-axis, which is the condition needed to have the origin or odd symmetry. So all conditions are being followed. This is therefore the graph of f of x.